Good morning, everyone. I want to welcome you to another statistical learning class. Of course, the focus today is, transforming the response. Well, for you to understand how we get into this particular topic of transforming the response, I think I'm actually going to have a recap on what led us here. Now, the story started, by trying to characterize relationship between variables, okay, one response and other predators. Now, you started by making an assumption, specifying the functional form of a model. And when you specify the functional form of a model, of course, your model is actually going to be a combination of deterministic and random component. The random component is the error, and of course, assumptions revolve around the errors. I remember assumptions of normality, assumptions of constant variance, and I also remember assumptions of, you know, absence of outlier, high leverage, and not only that, another assumptions. There's a lot of assumptions that we need to investigate. Now, when you specify your model, you estimate the parameters in your model. I mean, parameter in the regression model, and you after estimating that, you did what I call a model validation. The model validation can be achieved through regression diagnostics. So it's like you put in your model to test. You put in your model to test, you actually want to see whether your model, satisfy assumptions of normality, assumptions of constant variance, and so on like that. And of course, if you want to investigate or whether linearity assumption hold, you can use residual plot. And I remember I told you residual plot, for linearity assumption to hold, the residual plot must not show pattern. So you can also use residual plot to investigate the assumptions of constant variance. So residual plot can be used to investigate both assumptions of linearity and assumptions of constant variance. But if you want to investigate assumptions of normality, of course, you can make use of a normal QQ plot. Okay, you can look at the histogram. You can conduct a Shapiro-Wilk test of normality, of course, to be able to see whether error followed normal distribution or not. Now, after you've done all of that, you also want to investigate whether there is outlier and high leverage. And of course, I told you the other time, when you talk about outlier, we actually want to identify some observations, okay, with the extreme residuals. Okay, observations with the extreme residuals. And initially, um, residual was actually used to investigate whether there's outlier. So later, the story moved to using standardized residual. The standardized residual because there's possibility that the variance of residual may not be the same. And because of that, you standardize that. You have a standardized residual, and that has been used over the years. But let me also say this, in addition to that, we also have leverage. The leverage, can I identify some observations, whose their predictor value is very far from the means of predators. I want to identify some observations that have extreme values of X. X is the predator. If I want to do that, of course, I told you, you need to compute art matrix. The diagonal of Hart matrix will give the leverage of each observation. And of course, you can actually compare the the leverage of each observation with a particular threshold. Okay, I think I gave you the threshold in the lecture the other time for small, the one you use for small sample and the one you use for, large sample. And of course, I also told you Cook distance. Okay, I also told you that Cook distance, Cook provided us a formula that can actually be used to see whether outlier and leverage will be influential. Okay, he actually estimates the regression parameter, okay, with all observations, and also estimated regression parameter, leaving out some suspected observations that could be influential. And at the end of the day, he actually called that CI. Okay, so which means you're actually going to compute a Cook distance for a particular observation, and you have a threshold to compare that with. So you can when it is greater than 0.5 or when it is greater than 1. And of course, we did all of that. Now, statistics is like a story. The story continue even if I've done all of that. I also need to investigate whether there's a problem of multicollinearity. And that was what we did on Monday. Okay, the problem of multicollinearity need to be investigated in a multiple linear regression where we may be suspecting that the predators may be correlating. When they are correlating, they're actually going to be giving the same statistical information, and that will be problematic. Now, and the reason why it's going to be problematic is because, let me tell you this, the regression, the estimate of regression parameter, they're still going to be unbiased, but they're never going to be consistent anymore. And what we use to measure consistency, we use minimum variance. It means they are no longer going to have minimum variance. And if the variance of an estimator does not have a minimum variance, then that is very, very crucial in statistical setting, because we use the variance of an estimator a lot. Because when I find the square roots of the variance of an estimator, I have a standard error. And that standard error can be used to test hypotheses about regression parameter, can also be used to construct confidence interval about regression parameter. So the moment the variance of an estimator is messed with, it's actually going to affect the standard error, and it's going to affect our inference. And that is the reason why we actually need to investigate each predator, okay, to see whether they have a tendency of inflating the variance. And that is when, in that regard, I need a VIF. Okay. Now, for each explanatory variable, I'm actually going to compute the VIF for them. And I'm going to compare the VIF. We've got a threshold of 5. It is more than 5. That predator is problematic, and something needs to be done. I give you an example of situation that could lead us into multicollinearity. It could be when you are using a categorical predator and that have levels, and you use all the levels. If you use all the levels of categorical predator, you're actually going to fall into a dummy variable trap. A dummy variable trap will lead us to problem of perfect multicollinearity. In a perfect multicollinearity, you are not able to determine the determinant of your design matrix, and the inverse is not going to exist. Therefore, you may not be able to estimate parameters. But situation where it is not severe, where the multicollinearity is not severe, you are still able to estimate the regression parameter, even though they're still going to be unbiased, but they will no longer be consistent. I think that was what we did on Monday. But the story continues. Statistics is like a story that goes on and on and on. Now, for instance, if I subject my model to diagnostic testing, and I realize that there's a violation of assumption, that I need to fix the model. If there's a violation of assumption and you ignore that, and if you make recommendation based on your result, you're actually going to mislead. And that is the reason why whenever a problem exists, then we need to fix the problem. Now, the topic that we want to talk about today, transforming the response, is an attempt. I'm actually going to call that a transformational attempt to fix a problem in a model. Does that make sense? Now, I want to welcome you to transforming the response. At times, when violation exists, okay, when violation exists, maybe what is responsible for that violation is because the random variable, the response is not in a good statistical form. I'm going to say that again. At times, okay, the reason for violation, okay, violation could be attributed to the fact that maybe the response variable is not in a unique statistical form. And that was why I said here, I said the way the data are collected in our data set may not necessarily reflect the way we should use the data in our linear model. Okay, at times, the way we collect the data may not be the way we're going to use it. And probably something needs to be done. And that is what we call transformations. We could decide to transform the response. We could decide to transform the predators, but the focus today is on transforming the response. Okay, and that was why I said transformation of the response and the predators, okay, that we're actually going to discuss later, will improve the fit and correct the violations of model assumptions. But what are the assumptions that are likely going to be corrected? What are the problems that are likely going to be fixed transforming response variable? Okay, there are two. When the assumptions of linearity is violated, we can transform the response. When the assumptions of constant variance is violated, we can also, it's a good idea to transform the response variable. Now, let me tell you this. We all know how to investigate whether assumptions of linearity is violated or assumptions of constant variance is violated. If I want to check for linearity assumption, I can construct a scatter plot, which is a diagrammatical plotting of y against s. Looking at the scatter plot, I'll be able to see whether it's a straight line or not. I can also use a residual plot. Okay, using a residual plot, if the residual plot show a pattern, then I'm going to say there's a violation of linearity. I can use a residual plot to also investigate whether assumptions of constant variance is violated or not. So whichever way you want to go, if you identify a violation, how do we fix it? So instead of us to consider why the way it is, we can decide to transform y. And one of the way to transform y is to take a log, the logarithm of y. Somebody else can say, okay, let me take a square root. We can use different kind of transformation on y because we believe that y, the response variable here, is not in a unique statistical form. And when a random variable is not in a unique statistical form, it's actually going to cause a problem. Now, if I take a log of y here, and which means if this is the model with the error, the predicted model is going to be this. Now, the predicted model is actually going to be log y cap, blah, blah, blah. If I want to get my y cap back, you know what I'm going to do? I'm taking the log of, I'm taking exponential of both sides, solving that, I'm actually going to have that. My y cap now equal exponential raised to power that. So what are we trying to say? We are trying to say the error term does not enter the model additively, but the error term enters the model multiplicatively. That's what I mean. Is there any question? And if you take a look at initially when we plot y against s, it's looking like that. Because of that, we are suspecting violation. Then after we take the log of, when you take a log of y and take a log of s, we could have some transformation that will involve taking the log of y and taking the log of s. And look at what we have. But let me tell you this. We have identified a special technique in statistical literature that will enable us to transform our response variable when it is not in a unique statistical form. Okay, we actually call that a Bose-Cos transformation. This is not the only transformation we have in statistical literature, except that this is kind of common. So Bose-Cos transformation is actually a popular way, okay, to determine a convenient transformation on the response variable y. And we're actually going to introduce this. We're going to say y raised to power lambda. And if lambda is not equal to 0, it's going to be this guy. And if it is equal to 0, it's going to be log, which means when lambda is 0, then it's a log transformation of y. When lambda is not equal to 0, it's going to be this guy. But what if in a situation where lambda equal to 1? If lambda equal to 1, for instance, if I plug in 1, y raised to power 1 equal to y, then it's telling you you do not need any transformation. Y is already in its unique statistical form. Any question? Okay, now to be able to obtain, which means from data set, we need to optimally obtain lambda. We need to optimally obtain lambda. Okay, now if we want to obtain lambda, we can go by a way of maximum likelihood, where now if you take a look at this guy, okay, if you take a look at, this is what we're programming, okay, using the architecture of a normal distribution. Equation 16 will actually give you the log likelihood function of the distribution, putting into consideration or incorporating a Bose-Cos transformation. Okay, but I'll tell you this. We have a way to figure this out in R, using software R, or whatever software you prefer using. Now, we actually, whatever values of lambda that we have, for easier interpretation, we're actually going to run them to be this, either -1, 0, half, and so on like that, for easy interpretation. And I'm actually going to show you how, using example. Okay, now this is synonymous with I'm actually testing hypothesis, where I actually believe, oh, my lambda should be a particular value, okay, against the alternative that it is not that value. So which means we have to have a way to statistically test, okay, the appropriate value of lambda that is going to work. And not to, and that very test will follow a chi-square test. If I want to actually take a decision, then I can also construct a confidence interval and look at the interval to see whether the peak the pickedness, the maximum fall in the interval. Now, I need you to pay attention right now, and I'm actually going to demonstrate this using an example. Consider, for instance, the saving data set in a faraway package. You can have access to that data set in our, it's our build, it's our inbuilt. If you load a faraway package in R, you're actually going to have access to the data set. Okay, that collects information for 50 different countries. I'm actually going to show you variables in the data set. We have SR, which is the saving rate. Okay, saving rate, the POP 15, with the percent population under age of 15, POP 75, percent population over age of 75, DPI, per capita disposable income in dollars, and DDPI, percent growth rate of DPI. And SR, the saving rate, of course, it means the personal saving divided by disposable income. Okay, now this is the first six in the data set. Okay, but the interest here is we actually want to look at the relationship between the saving rate. The saving rate is the response, okay, in relation to other variables. And we actually want to have a sense of what lambda value is going to work if we use a Bosco transformation. Maybe there's a violation of assumptions of constant variance and linearity. You actually want to fit a linear model for this, and you suspect, or you after your regression diagnostics, you realize that a linearity assumption is violated and constant variance assumption is violated, and you want to use a Bosco transformation on the response variable. The response variable is the saving rate. You actually want to have the idea of a lambda value that is going to work in the transformation. Now, I need you to pay attention to this right now. There's a code in R. Okay, if you take a look at, give me 1 second, let me clean up. Okay, let me see. Okay, now, if I want to use a bus clause, in the bus clause method in R, okay, I need you to pay attention to this. That you take a look at that code. Before I first run my regression, my linear regression, XR, on the other variables, I'm using a saving data set. Then I'm going to write a bus clause. Please pay attention. Okay, I'm actually going to write a bus clause. Can you see that? And finally, I'm going to write that. Okay, and I suggest a sequence for what lambda could be, probably from a 0.5 to 1.5. And this is, I have this particular picture now, but this one is the one that shows more clarity. You know what I need? If you take a look at what I'm actually going to, the interval here is from 0.6 to 1.4. You see the interval? It's the interval for lambda. Okay, 95% confidence interval for lambda is between 0.6 and 1.4. And you're actually going to see 1 fall between, right? 1 fall between 0.6 and 1.4, because 1 fall between that, then I may be saying I do not necessarily need transformation. Does that make sense? When lambda equal to 1, and that's what I mean here. That's what I mean here. When lambda equal to 1, y stay the same. What that means, y is already in a unique statistical form. Further transformation is unnecessary. Does that make sense? But what if in a situation, maybe after you've done all of that, you have this from negative 0.95 to negative 1.5. Okay. If you take a look at that, -1 lies in between, right? -1 lies in between, right? I'm going to pick a -1. And picking, it's not as if I can't pick any other number, but -1 will lead to easier interpretation. Now, initially, I have y raised to power lambda, and now my lambda equal to -1. Then it actually means y raised to power -1, which is the same thing as 1 over y. What does that mean? That's a reciprocal. Reciprocal. So which means if I want to rerun my regression, then I'm actually, instead of me to use y, I'm going to use a reciprocal of y. Does that make sense? With the reciprocal of y, um, the response variable is in a very good unique statistical form. Now, what if in a situation where I got -1.5 to -1.1? If you take a look at this, there is no -1 in this interval, right? There's no -1, right? Somebody can reasonably choose this. If you choose this, you're still going to have your problem solved. What problem is it going to be solved? Whatever value you choose within the interval, we have your problem addressed. But if you are not careful in what you are choosing, even though you succeeded in solving the problem of constant of non constant variance and of non-linearity, but you're actually going to run into difficult there's going to be difficulty in interpretation. Okay. And that was the reason why I said here, some people can decide to choose -1, even though -1 is not an interval, but very close to -1.1. Okay. And that's why I said that we choose that because of, we don't just want to solve a problem, but we also want our model to be interpretable as well. I don't know what happened. Whenever there's a problem, there's going to be an intervention. Intervention don't solve problem without creating additional problem. I'm going to say that again. Whatever intervention, whenever there's a problem, whatever intervention, no intervention solve problem completely. Or if it solves problem completely, then it has a tendency of inducing or introducing a new problem. And the new problem that is introducing now is a problem of a difficulty in interpretation. Does that make sense? Is there any question? Okay, what if in a situation where the interval is between -0.5 and 0.5? Obviously here, 0 lies in the interval. I'm actually going to choose 0, lambda equal to 0. Lambda equal to 0 implies a logarithmic transformation. Does that make sense? So it means I need to take the log of my response variable. And when I take the log of my response variable, it's actually going to be in a unique statistical form compared to the conventional Y reported. Now, bus cost transformation approach has really done a very great job, but okay, we have some considerations concerning the bus cost method as well. The bus cost method is affected by outliers. I just wanted to know that. It's not perfect. It's also affected by outlier. And if the ratio of the maximum response to the minimum value of response is very small, the box source will not have any significant effect. We don't just do what we do. It's not as if our models are failing us, but do we pay attention to detail? We don't just use a model recommendation from model in policy formulation like that without making sure that we've done everything that we are supposed to do. Why are we in a rush? We shouldn't be in a rush. And that is the reason why at times it's going to look as if our models are failing us. Our models are not failing us. We are the one that we're not doing a great job. And how are we going to do a great job? If I'm using a particular technique in statistical world, I need to for of us, understand what could be the limitation of what I'm using. Now, I said the Boss cost method is not the only way of transforming. We also have other way of transforming the response variable. We have Johnson transformations and so on like that. Somebody can pick up a research where maybe you have discovered that there's a violation issue with a model, and you now want to compare Bosco's transformation with a Johnson transformation to see which transformation technique is actually going to do a great job in fixing the problem. We have a way to investigate when the problem is fixed. So if I transform Y, okay, if I transform Y for whatever value of the lambda that I come up with, then I actually going to go back to conduct a regression diagnostic testing to see whether the problem still persists or the problem has been fixed. The same way, how is a medical doctor is going to know whether he or she has successfully treated a patient before when the patient comes in, they have a measurement, they run a laboratory, testing and so on like that. And after they have, administered, medicine, they're also going to run the test again, to see whether the problem is still there or not. We do the same in statistical world. Okay, and let me also say this. In addition to transforming Y at time, because transforming response variable at time may not solve the problem, maybe we also need to transform the predator as well. Okay, and let me also say this. We transform the response variable here, seeking the maximum value of lambda. I'm going to say that again. We use the method of maximum likelihood, okay, to arrive at an optimal value of lambda. Do you know can we also use another approach? We maybe the approach of the least square, the approach that will minimize the residual sum of squared. If we use the approach that within the same Boss cost transformation, if I actually figure out my lambda using the approach of maximum likelihood, and I also figure out my lambda using the what I call the least square approach, where the intention is to minimize the residual sum of squared, do I get the same lambda? You can also do that as well. Okay, what am I having next? What I'm having next is a model selection. I got different kind of models, and how do I know which one is the best that I'm actually going to use? Then we're going to talk about if I have so many features in a model, and because of the fact that we're going to run into mathematical complexity that will induce over parameterization that is also going to be responsible for over fitness. Can we have a way to regularize our model? We're also going to talk about the ridge and lasso regularization. This is where I'm actually going to stop today. Is there any question before I go? Is there any question? Now I have a very vital information announcement to make. The midterm one and the midterm two, instead of us having it on Friday, I've shifted it to the next Monday. You know what I mean? Like this, like it's not going to happen that Friday. It's going to happen the following Monday. The reason being that we got some students that are, that exam is clashing with another. It's not as if it's clashing with another exam, but it is like when they finish writing this exam, they're going to write another exam, and because I've been student before, that is not going to be easy. So check the syllabus. I've already updated the new dates for exam one and exam two. Instead of it happening on Friday, it's going to happen the following Monday. Does that make sense? Make sure you all stay safe. Have a lovely day. Bye for now, everyone.
Thank you.
You're welcome. Have a good day.